Greetings everyone, and welcome back to our online lecture series for CHE 2300. In today's lecture video we are going to discuss the equations necessary to describe heat transfer in multiple pass heat exchangers. And so up to this point we have either discussed or dealt with single pass shell and tube heat exchangers or double pipe heat exchangers, which are by default a single pass heat exchanger. And what we saw from our discussions was the following design equation, which can be used to describe the heat transfer rate in our heat exchanger, which is a function of the overall heat transfer coefficient, either based on the inside or outside area of the tubes, the total area required for heat transfer, which again is based on either the inside or outside area of the tubes, and the log mean temperature difference of our heat exchanger, which again accounts for the fact that the temperature difference or gradient across our heat exchanger is not necessarily linear. Unfortunately, when we have multiple pass heat exchangers, to account for things like different flow patterns, equation 1 is not always valid. And so to take into account all of the flow effects, we introduce a corrected design equation, which looks very similar to the previous equation. So we have our heat transfer rate is equal to U A sub t delta t log mean, and the only thing we're going to do here is introduce a correction factor, F sub g. So here F sub g is equal to some correction, right, or fudge factor for our heat exchanger. Okay, so the equation again is analogous to equation 1, except for this additional correction factor that again is there to account for the flow effects that occur when we have multiple pass heat exchangers. Then the question becomes, how do we determine that correction factor? So the correction factor can be determined or calculated directly using the following equation. And if you bear with me, this is a relatively large equation, so it's going to take me a bit to write it down. So on the denominator we have c minus 1 times the natural log of 2 minus eta sub h. That is multiplied by z plus 1 minus z squared plus 1. Whoops, that is going to be raised to the half power. And then that is divided, let me close my parentheses. Okay, then we have 2 minus eta sub h, z plus 1, and the only difference in our term down here is we have a plus z squared plus 1 to the 1/2. Okay, that's on our denominator, and so in our numerator we have a z squared plus 1 to the 1/2, and that is multiplied by the natural log of 1 minus eta h, and that is divided by 1 minus z times eta h. Okay, and so again we can use equation 3 here to directly calculate our correction factor F sub g. as long as we know our parameters, Z and A to H. So what are Z and A to H? So Z is equal to the mass flow rate and the specific heat of our cold stream divided by the mass flow rate and the specific heat of our hot stream, which is all equal to the temperature difference of the entering and exiting hot streams, or hot stream, I should say, and the temperature of the cold stream leaving minus the temperature of the cold stream entering the heat exchanger. Our eta sub H term is what we are going to call our heating effectiveness. So eta sub H is equal to the temperature of the cold stream leaving minus the temperature of the cold stream entering the heat exchanger divided by the temperature of the hot stream entering the heat exchanger and the temperature of the cold stream entering the heat exchanger. And so what this heating effectiveness term describes is the actual temperature rise of our cold stream divided by the maximum possible rise. So again, the numerator here, this is the difference between the cold stream leaving, the temperature of the cold stream leaving the heat exchanger and the temperature of the cold stream entering the heat exchanger, so the actual temperature rise of our cold stream, and that is divided by the maximum possible rise that we could achieve if the entering cold stream and the entering hot stream had the same temperature. Excuse me, I said that completely wrong. The maximum possible rise here represents the maximum possible temperature difference between the entering hot stream and the entering cold stream. Right, so this term is what we're going to call our heating effectiveness. If we know Z, we know our heating effectiveness, we can directly calculate our F sub G term from equation 3. We can also read our F sub G term off the charts that you see on this page. So here we have a correction factor for 1 and 2 shell passes. So here we have our chart for 1 shell pass, and below we have our chart for 2 shell passes. And so if you read what the statements say, the top one says this correction factor is for 1 shell pass and 2 for or any multiple of tube passes. And so this is oftentimes referred to as a 1-2 heat exchanger. Again, meaning we have 1 pass on the tube side and some multiple of 2 passes on the tube side. 1 pass on the shell side, some multiple of 2 passes on the tube side. On the bottom, we see here that this is the correction factor for 2 shell passes and 4, 8, or any multiple of 4 tube passes. And so this is oftentimes referred to as a 2-4 heat exchanger. Again, 2 passes on the shell side and some multiple of 4 passes on the tube side. And so if we know our heating effectiveness, We have that plotted on our x-axis. On our y-axis, we have the correction factor, and then these various lines that you see on our plot represent our z parameter. Okay, so these are for shell and tube heat exchangers. I can have a similar plot for cross-flow heat exchangers. So the correction factor for a cross-flow heat exchanger where both fluids remain unmixed is what we have in our top chart or figure, and in the bottom figure we have another cross-flow heat exchanger chart, but in this case one of the fluids is mixed. Okay, so we haven't talked much about cross-flow heat exchangers. All I want you to know is that we have these correction factors for cross-flow heat exchangers in addition to our shell and tube heat exchangers. One fluid unmixed, which is the same thing as one fluid mixed, but that's typically how it's discussed. Are both fluids unmixed, or is one fluid unmixed? Okay, so that's really all I want to say about multiple pass heat exchangers. The design equation is very similar to what we have seen before. The only additional term now is this correction factor. We can again calculate that correction factor based on this equation, or we can pull our correction factor off a chart. Okay, so let's do an example problem so you can see how we might apply these particular equations. So in the following example problem, we have some oil. That oil is being cooled by passing it through a countercurrent heat exchanger, and we're going to use some cooling water to cool that oil down. In this case, we have a single pass heat exchanger. So this is the same example problem that we saw from the last lecture. We had oil, it entered at 375 K, it left the heat exchanger at 350 K. We had some heating water entering the heat exchanger at 280 K, and if I'm not mistaken, it left the heat exchanger at 318 K. All of those parameters are the same, and again we're going to assume adiabatic operation, where all of the energy lost by the hot stream goes into heating the cold stream. Okay, so now let's imagine the scenario. So here we have a new scenario. We are going to move to one shell pass, but now we are going to have 4 tube side passes. Okay, so we no longer have a single pass heat exchanger. We have a 1-2 heat exchanger because, again, we have one shell side pass and some multiple of 2 tube side passes. We are going to assume that everything else in our problem remains the same. So the entering and exiting temperatures of our hot and cold stream are going to remain the same, and our overall heat transfer coefficient is going to remain the same. And the question becomes, if everything remains the same, but in this case we have a 1-2 heat exchanger that has 4 tube side passes, what is the total area of heat transfer required for those conditions to remain the same. Okay, so the first thing we're going to do is calculate Z and eta sub h. So here again, Z equals the temperature of the hot stream entering, temperature of the hot stream leaving. That is divided by the temperature of the cold stream leaving minus the temperature of the cold stream entering the heat exchanger. All of that is equal to 375 minus 350K. Divide that by 318 minus 280K. And again, this is also equivalent to m dot Cp of the cold, m dot Cp of the hot. Right. All of that is approximately equal to 0.66. Okay, so we have Z. The next thing we need to calculate is eta sub h. Our eta sub h is equal to the actual temperature rise of our cold stream divided by the maximum possible rise that our stream could achieve, which is the difference between the hot stream entering and the cold stream entering the heat exchanger. So here this is equal to 318 minus 280K, and that is divided by 375 minus 280K. If I do the math on that, I get an answer that is approximately that is approximately 0.40. Okay, so Z equals 0.66, eta sub h equals 0.4. We're going to move back up to our charts here. Let me erase all of this. Okay, and the first thing we're going to ask ourselves to determine which one of these charts to use is how many shell side passes do we have? Do we have one shell side pass, or do we have two shell side passes? The problem statement says that we have one shell side pass, so again we have a 1-2 heat exchanger. So let's zoom in a bit on this. Okay, so our eta sub h is about 0.4. We are going to find our line for 0.6. Find our line for 0.7, because we're somewhere right in the middle of that, and what you see is by the time this thing gets to around 0.4, those lines essentially converge. Where do they converge? They converge somewhere around 0.96 for our correction factor. So let me come back down to our problem. From figure 15.6a in your textbook, so McCabe, Smith, and Harriet, our correction factor is approximately 0.96. Alright, so our design equation for multiple pass heat exchangers is Q sub T. Our rate of heat transfer is equal to our correction factor multiplied by our overall heat transfer coefficient multiplied by the total area of heat transfer. This, of course, is what we are trying to find, and that is multiplied by the log mean temperature difference. So let me just rearrange this equation for the term we are trying to solve for. So we get the total area of heat transfer is equal to the rate of heat transfer, and that's divided, and that is divided by our overall heat transfer coefficient multiplied by our log mean temperature difference, and then of course we have our correction factor. So let me plug in all of the numbers. For the QT, it doesn't matter which stream we pick since we're assuming adiabatic operation. So I'll pick the hot stream, so 0.6 kilograms per second multiplied by the specific heat of the hot stream. That's going to be multiplied by the temperature drop of our hot stream. Okay, that's going to give us the rate of heat transfer divided by our correction factor of 0.96, our overall heat transfer coefficient of 250 watts per meter squared Kelvin, and then the log mean temperature difference. We calculated this because, again, this is the same example problem we did in the last lecture. The entering and exiting temperatures of the hot and cold stream are not changing. Therefore, the log mean temperature difference of our heat exchanger is the same as the last problem, which we determined to be 63.3 Kelvin. If I've done my math correctly, the total area of heat transfer that is required for our one shell side pass and 4 tube side pass heat exchanger is 2.06 meters squared. This value is approximately 4% larger than the total area required for heat transfer that we calculated in the previous example problem where we only had a single pass heat exchanger. Okay, so hopefully that made sense and you got an idea of how we might apply this correction factor to calculate a particular parameter involved in these multiple pass heat exchangers.